Hey guys, it's Miss Sullivan talking about terminating and recurring decimals. So, just a quick little reminder like I do all the time. Those drawings are meant to be identical. Of course they are, let's just pretend. So in the classroom, my name's Miss Sullivan. In the staff room, my name's Antonia. At home, my name's Mum. And in the car, fool is, well, it's a nice way of saying what some people might yell out at me. Not because I'm a woman driver, but because Antonia is patently bad at driving. Not because she's a woman. Those two things are not related. We'll find out more about that when we do ratios. So, what we're talking about is terminating and recurring decimals. A little reminder that different names for different contexts, classroom, staff room, home, car, but the same person. Just like a half is equivalent to 5/10, which is equivalent to, I can also express that as 0.5. That's 5/10, and that's 5/10. So just a little reminder, quick check-in with place value. So we learnt this when we were tiny. There's our decimal point, and all the whole numbers are on this side. Ones, tens, hundreds, thousands, 10,000, 100,000, millions, I go on and on and on. We've also learnt that 10 to the power of 0 is 1. 10 to the power of 1 is 10. 10 to the power of 2, 100. 10 to the power of 3. Think about if that was 1,000, it would have 1, 2, 3 zeros. 10,000, 10 to the power of 4. If that was 1, there'd be 1, 2, 3, 4 zeros. 10 to the power of 5 for 100,000. So let's count the zeros. 1, 2, 3, 4, 5, 6. This is 10 to the power of 6. So there are whole numbers. When we're looking on this side of the decimal, we're looking at parts of numbers. Tenths, hundredths, thousandths, 10,000ths. You'll learn more about this next year, but for now it's important to just remember, well, it's interesting to just remember that this is 10 to the power of -1, 10 to the power of -2, 10 to the power of -3, and so on and so forth. So just a little reminder about our place value, because we need to come back to that when we're adding and subtracting decimals. But for now, let's find out a bit more about decimals. So let's have a look here. If I've got a half, we know that that line really means divided by. So 1 divided by 2, 2 into 1. 2 into 1 I can't do. So the decimal system allows me to pop in a decimal and add a 0. So there'll be nothing in the ones column because it doesn't fit. And I've got my little remainder 1. So because I wasn't able to do anything with it. So 2 into 10 goes 5 times. This is what we call a terminating decimal, because it's possible to create from a half some sort of fraction that's got 10 as its base. So what I mean by that is, if I've got 1/2, it's easy to create an equivalent fraction with 10 on the bottom. To get to here, I times that by 5. So if I times the top by 5, I get 5 over 10. And because it's the decimal system, dec literally means 10. And we've talked about this before in class. We have a decimal system based on base 10. So this is what base 10 looks like. Everything's base 10. You get one of these, 10 of these, one of these, 10 of these, one of these. Everything's based on base 10 because we have 10 fingers. So if I've got 5/10, it's 0.5. That decimal terminates. It comes to a nice little neat end. When we're thinking terminating decimals, so they're decimals that I can express with a base 10 on the denominator. So they terminate. So I like to think about terminals at the airport where your flight terminates. So let's have a look at this one. 3 over 4. Can I create an equivalent fraction with 10 on the bottom? No. So I'm going to have to go to, that's 10 to the power of -1. I'm going to have to go to 10 to the power of -2. I'm going to have to go from tenths to hundredths. Oh, and now I can do it. And I can see that that is 4 times 25 equals 100. So 3 times 25, what I do to the bottom, I do to the top to create an equivalent fraction, is 75. So that is 75 hundredths. It's a lovely, neat terminating decimal. Let's have a look at the next one, which is 3/8. So can I create an equivalent fraction with 10? Nope. 10 to the power of -2 with 100? Nope. What about 10 to the power of -3 with 1,000? Well, I know that I can. But I'll just cheat for a second and we'll pretend that we didn't do that and that this wasn't something that everybody worked out earlier. And we'll have a look here and we'll say 1,000 divided by 8 is, 1,000, is 125. So if I had to multiply that by 125, sorry, that's a bit dark and everything's moving. I'll just try making it a bit brighter. I hope that's better. Then 3 times 125 is going to equal 375. So 3/8 is equivalent to 375 1,000ths. Cool. I'll try and do this a different way to work it out because, that's like a trial and error thing. So at the moment, I'm going to try and work it out by doing 3 divided by 8. So 8 into 3. So here I'm going to go back to this little fraction, this little decimal trick that I can do here. I can't do nothing. 8 does not fit into 3. So we've got a 0, doesn't fit in. And I'll add my first 0 in the tens. So 8 into 30. 8 into 30 I can do. And 3 times 8 is 24. And 30 minus 24, well, let's just practice doing actual subtraction longhand. 0 take away 4 I can't do, so I'm going to take a 1/10 from you. So 10 minus 4 is 6. Now I need to add another 0 because 8 doesn't go into 6. So I'll bring that 0 down, 8 into 60. Oh, 8 does go into 60. 8 goes into 60 7 times. 7 times 8 is 56. All right. So let's have a look at what I've got now. I'll just put a little minus up just to remind us about long division. So 0 minus 6, I can't do that. So I'm going to have to take a 10 from there. 10 minus 6 is 4. 5 minus 5 is 0. Well, 8 doesn't go into 4, so I need to add another 0, and I'll bring this 0 down. Oh, 8 into 40? 5 times. So it is possible to create a terminating decimal out of 3/8, even if I don't know anything about multiples of 8s, like 8 being multiplied 125 times to get to 1,000. So let's have a little reminder there. Our terminating decimals are decimals that wrap up neatly. So sometimes if we can create an equivalent fraction with 10 at the bottom, it'll be tenths. With 100 at the bottom, it'll be hundredths. And with 1,000 as the common denominator, in the thousandths. So that's nice little neat terminating decimals. The other type of decimals that I have are recurring decimals. So recurring decimals go on forever in some kind of pattern. So a third's a really good example. It's 0.333333. And why is that the case? Because obviously I can't do anything where 3 is going to have a common denominator being 10 or 100 or even 1,000. So I can't create a common denominator with anything that's remotely base 10. So what I'm going to do is I'm just going to put a question mark there so that we remember. It's not going to work with 10, it's not going to work with 100, it's not going to work with 1,000. Getting where I'm coming from? So now let's do the sum. 3 into 1. So 3 into 1 doesn't go. This time I'm not going to do long division, I'll just do it shorthand. 3 into 10 goes 3 times. Oh, but that's 9. Remainder 1. 3 into 10 goes 3 times. Oh, but that's 9. So there's a remainder 1. 3 into 10 goes 3 times. Oh, but that's 9. So there's a remainder 1. Oh, 3 into, I've still got this remainder 1. And as you can see, it's going to continue on forever. So 1/3 equals 0.3 forever. That one little 3 is going to go on indefinitely. That's what we were doing in the last, the little sneak peek from the last video. Let's have a look now at 5/6. Now I'm going to just jump straight into doing it this way. I'm not going to try and create a common denominator with 10 or 100 or 1,000. I'm just going to write it as, so is equivalent to 5 divided by 6, 6 into 5. I can already see it's going to be painful. So 6 doesn't go into 5, 0 pop down our decimal. 6 does go into 50. It goes into 50 8 times. 8 times 6 is 48. 50 minus 48 is 2. Let's add that 0 and bring it down. 6 into 20 goes 3 times. 3 times 6 is 18. Oh, we'll need another 0 because we're going to be left with a remainder of 2. So bring that 0 down. 6 into 20 goes 3 times. 3 times 6 is 18. Take that away. Remainder 2. Oh, I need another one. And I think we can see where this is going. 6 into 20, 3 times 16, 18, 20 minus 18, 2, add another 0, bring it down, 6, and it will continue forever. So 5/6 is 0.8, and the 3 goes on forever. So notice that I only put the dot over the top of the 3. Does that make sense? It's a recurring decimal. It's going to go on for forever. Forever, I'm going to be saying 3 times 6 is 18, remainder 2, create another decimal place, 6 into 23, 3 times 6 is 18, remainder 2, and it would just go on and on and on. Let's have a look at one that's a little bit more complicated also, so that we can just get a little bit more practice with long division. And we'll have a look at 7/12. So again, we're just going to say 7/12 is the same as 12 into 7. Can't do it. And I've started. So 12 goes into 70 5 times. 5 times 12 is 60. That's going to leave 10. We'll add our 0 and we'll bring this down. 12 into 100. 12 into 100 goes 8 times. 8 times 12 is 96. 100 minus 96, I've got a remainder of 4. Okay, so I need another 0, and I'll bring my 0 down. 12 into 40. 12 into 40 goes, sorry about this, I'm having phone issues. Okay, 12 into 40 goes 3 times. 3 times 12 is 36. 40 minus 36 is 4. Add another 0, bring it down. I think you can see what's happening again. 12 into 40. 3 times 12, 36. Oh, look, I'm left with a remainder of 4. Add another 0, bring down the 0. 12 into 40, 3 times 12 is 36, and I'm going to end up with a remainder of 4, and this is going to continue on for forever. So this equals 0.583, and the 3 goes on forever. So as not to kill you with more long division, which I'm sure is fascinating to watch, let's use our calculator and cheat a little bit. So we're going to enter in 17/33. So 17, little fraction button, 33. Then you just hit the equals button. So that's what I did then. I hit equals after I did that. So that I can hit this little button here, S to D, which will turn my fraction into a decimal. And as you can see, this one goes 5, it'll turn it back too. So as you can see, it's 0.5151515151552. So it's just done a little bit of rounding for us because this is a recurring decimal, but it's recurring in that pattern of 5-1. 5-1-5-1-5-1-5-1-5-1. So I put a little line above the 5-1 And I know that it occurs like that indefinitely. Well, basically for infinity. 0.5151515151, and I think we all get the picture. So, really important to know what terminating and recurring decimals are because it makes them easier to use. But it's also important to understand these things because not only do we have the funky decimal system, but our number system is also based on categorizing it's based on categorizing numbers not just as they're represented by the base 10 system. So real numbers, all real numbers, the set of real numbers are represented with the letter R. And most of them are rational numbers, which are represented with the set Q. So Q stands for all of your rational numbers. Rational numbers are your integers, like you learnt last term. Integers, every integer represented as the set equals Z. The whole set of integers is Z. So integers are 0, positives, negative numbers. So 0, your positives, and their opposite negatives, as well as terminating and recurring decimals. So that's most real numbers, but there are irrational numbers represented with the letter I. So all irrational numbers are represented as set I. And irrational numbers, even though there's more of them than these, one major form of irrational number is non-terminating and non-recurring decimals. So basically, these might go on indefinitely, but they do so in a pattern. These ones terminate, they wrap up nice and neatly, and then there are non-terminating, non-recurring decimals that go on for forever in no pattern. Things like pi. So 3.1415, and it continues on forever with no repeating pattern. Kind of cool, hey? So pi is irrational. That's just something that's really interesting to know. It's not something that's going to be on your exam. Cheers!